Earth is considered the optimal planet in the universe multiple times. No other place in the universe surpasses Earth as a suitable habitat. This superiority is attributed to the fact that both humans and other earthly organisms have evolved here. Our adaptation to life on this specific planet, resulting from the process of evolution, makes it unlikely for us to thrive as well elsewhere. However, if we broaden our perspective beyond our species, are there locations in the universe that could support a more diverse range of life forms? It is remarkable that life exists on Earth at all. We are fortunate to have originated near a main sequence star with a moderate number of flares. The planet boasts an atmosphere abundant in oxygen and nitrogen, enabling us to breathe. Additionally, the planet's size prevents the core from cooling, ensuring that its outer part remains in a liquid state. Convection currents of metals in the planet's interior generate a magnetic field akin to the protective shield provided by the dense atmosphere, guarding the planet's surface against cosmic rays, intense ultraviolet radiation, and potentially devastating solar storms. Plate tectonics continually reshape the rocks of the lithosphere, bringing new elements to the surface from the subsurface. A moderately large satellite, our moon, likely plays a crucial role in maintaining the planet's axial tilt and governing the tides that facilitated the migration of early life forms from oceans to land. The presence of our moon has additional benefits. The expansive oceans play a pivotal role in regulating the planet's climate, redistributing warm waters to colder regions and thereby creating favorable conditions for life. These advantages, along with others yet to be discovered, have allowed life on Earth to thrive, adapting through the process of evolution to extreme conditions such as bitter cold, scorching heat, the immense pressure at the ocean floor, and even the environments created by humans' neighborhoods. Considering the possibility of superhabitable planets prompts us to reevaluate our perception of uniqueness in the cosmos. Astronomy has dispelled the notion of our centrality, revealing that Earth is not situated at the solar system's core and does not occupy a singularly exceptional position in space or time. This realization suggests that Earth may not be an ideal habitat, despite being optimal for human life. In a 2013 paper, astrobiologist Ravi Kumar Koparapu and his colleagues from the University of Pennsylvania established habitable zone limits around stars based on contemporary climate data. Their calculations indicate that the habitable zone around a star like our Sun spans from 0.99 to 1.7 astronomical units, measuring the distance from the Sun to the Earth. Remarkably, our planet resides on the outer fringe of this zone, where life can flourish. Our fortune lies in this proximity, as a slight shift could subject us to the same greenhouse effect experienced by Venus. Optimal living conditions are more likely to be found closer to the center of the habitable zone, minimizing the risk of adverse consequences from orbital fluctuations. Life on Earth can be considered relatively young, with the planet's existence spanning only 4.5 billion years, and the emergence of multicellular organisms occurring in the last few 100 million years. As the Sun gradually heats up, our proximity to it gives us only a limited window, perhaps a few 100 million years, at most a billion, before all the water on Earth evaporates. However, what if life had the potential for billions of years of evolution, paving the way for the emergence of new and more diverse forms of living entities? Consider the possibilities if Utkanos seems peculiar to you. Envision the outcomes of another 2 billion years of evolution, or even after 20 billion. Recently, Rena Heller and John Armstrong explored this concept in their paper on superhabitable worlds, outlining the optimal conditions for the development of life beyond our planet. The authors suggest that stars with masses slightly less than the mass of the Sun, in particular K-class stars, have more favorable conditions for the development of life. These stars are relatively stable and have long lifetimes, from 20 to 70 billion years, and mega flashes, characteristic of red dwarfs, do not occur. In addition, the habitability of these planets can be enhanced by an influx of asteroids with the substances necessary for life, such as water. Ideally, such a system would have several habitable planets capable of exchanging life forms, a process called panspermia. If the planet orbits a gas giant, powerful tidal forces can support constant volcanic activity, The situation is even more favorable in a double planetary system where two worlds orbit around each other, creating tidal forces and facilitating the exchange of life forms. Going even further, increasing the size of a planet gives more room for the water cycle and the movement of cold and warm currents. An ample range of niches for new life forms becomes available on a planet, but there exists a limitation to its size. When a planet's mass doubles that of Earth, the movement of tectonic plates slows down. Therefore, moderation is key. Sufficient size is necessary to maintain a hot core and the movement of conductive layers around it, thereby sustaining a planet-wide magnetosphere. Considering gravitational force near the surface, a 40% increase in size is adequate to maintain the same gravitational force experienced on Earth with double the mass. Crucially, the role of oceans appears pivotal in determining whether a planet can be classified as superhabitable. At the 2019 Barcelona conference, Dr. Stephanie Olson from the University of Chicago shared findings from research aimed at identifying an optimal hypothetical environment for sustaining life on exoplanets. Her team utilized a NASA tool that employs modeling to simulate the climate of a given planet. This remarkable program is freely accessible, allowing users to explore the climatic conditions of various celestial bodies, including ancient Venus or planets orbiting Proxima Centauri. The tool provides a comprehensive set of parameters, including temperature, precipitation, surface properties, and more. For instance, users can examine Earth's conditions during the pre-industrial era, where air temperatures were approximately 35 degrees Celsius near the equator and minus 60 degrees at the poles. Additionally, one can investigate ancient Venus, depicting conditions 2.9 billion years ago when the sun was 20% dimmer than its present state. Even in its ancient past, Venus completed a full revolution on its axis in 243 days, likely accompanied by an ocean with a maximum depth of only 310 meters. Now, consider a planet orbiting the red dwarf Proxima Centauri, the nearest star to the Sun. Due to its small orbital radius, this planet is likely in a tidal lock, always presenting the same side to the star. This characteristic significantly influences the temperature distribution in its atmosphere. However, if this planetary system exhibits orbital resonance, where the planet completes 3 full revolutions for every 2 orbital passes, and if its atmosphere is roughly similar to Earth's nitrogen-oxygen atmosphere, it could potentially offer a reasonably comfortable environment for habitation. Olson and her team utilized the software to simulate the climate and ocean conditions of various exoplanets. On Earth, the diversity of life is intricately linked to nutrients, rising from the ocean depths to the surface, creating an environment that supports a wide array of organisms. The presence of more water correlates with increased biological activity and diversity. Essentially, planets with a multitude of sea currents should exhibit the greatest biodiversity. According to Olson's research, the optimal conditions for ocean circulation on a planet are influenced by the presence of continents, with slower rotation and denser atmospheres, enhancing this circulation. These findings provide valuable insights for astronomers as they explore planets beyond our solar system. Several missions, scheduled for the late 2030s, aim to directly image exoplanet surfaces, analyze their atmospheric chemical compositions, search for water, and assess the extent of continent coverage on these distant worlds. It would not be surprising if we discover super-habitable planets in the Milky Way that may outnumber Earth. This idea challenges the notion that the Earth is unique. That's fine. At least we'll have neighbors. Let me know in the comments what you think about it.